All right, before we begin, let me point out that this worksheet is meant to follow the 4.2 intro worksheet. So if you haven't already worked through that, I would strongly recommend you start with that. This one is going to be showing you how to get through 3 different rectangular area methods. That's what the RAM stands for. The R, L, and M at the beginning are right, left, and midpoint. So we've got the right rectangular area method, we've got the left rectangular area method, and we've got the midpoint rectangular area method. And each one of these is going to be a way of approximating the area under a curve, which turns out is a very common calculus question that you're going to be asked to solve. So, for example, on number 1, we're given the function x squared, y equals x squared, going from 0 to 1, so x equals 0 all the way to x equals 1. And we're going to try to approximate this area. So the shape looks kind of like a triangle, but obviously one of the sides is not a straight line. We're going to try to find the area of this region right here, including all these little white spaces up here. That's the goal, but not including all of those green corners that are sticking out. That's what we're ultimately interested in. And before we get into the exact area, we're going to start with approximations. So we're going to divide the shape into rectangles, and each one of those rectangles has the same width. How do we determine the width? Well, it tells us over here that we have 5 partitions. So we're going to take this interval of 0 to 1, and we're going to cut it into fifths. 1/5, 2/5, 3/5, 4/5, and 5/5. So we take the interval that we're interested in and we divide it up into, in this case, 5. It doesn't have to be 5. And each one of those intervals is going to be the base of a rectangle. You'll notice that each one of those bases is the same. The width of each rectangle is the delta x value of 1/5. X changes from 0 to 1/5, and then from 1/5 to 2/5, and then from 2/5 to 3/5. So our delta x is constant. It doesn't have to be constant, but for these problems we're going to leave it as constant because it makes things a lot easier. So you'll notice that 0.25, the 1/5 or the 0.2, that's going to be the width of each one of these rectangles. But the height is changing each time. And how do we determine the height? Well, the function is going to determine the height. If our function is low down to the x-axis, our rectangle is going to be very low. But if our function is taller, then our rectangles are going to be higher. And that's going to help us determine how high our function is. How high our rectangle is. So we are going to look at the fact that we're using the midpoint rectangle sum in this problem to say, okay, well, for each one of these rectangles, we're going to look at the little sub-interval, like, for example, from 0 to 0.2. We're going to look at the midpoint of that sub-interval. So the midpoint between 0 and 0.2 is 0.1. So that value of 0.1 is going to be the value we're going to use to find the height of our rectangle. Now, that height is a very small one. It's hard to see. So I'm going to jump to the very end. I'm going to look at the midpoint right here. The midpoint between 0.8 and 1 is 0.9. 0.9 is not the height of my rectangle. Rather, it's the x value that's going to determine the height of my rectangle. So if x equals 0.9, what does y equal? Well, we've got a function, right? We've got this function f of x equals x squared. So f of x equals x squared, f of 0.9 equals 0.9 squared, which is 0.81. And lo and behold, 0.81 right here is the height of that rectangle. So we're using the function f of x equals x squared, the given function, and we're using select x values to determine the height of each rectangle. So how does this table work? Let's see. Well, we've got partitions. We've got 5 partitions, so we start with the first, second, third, fourth, fifth. We'll worry about this last row in a second. These x values came from the midpoints of the subintervals, right? So 0.1 is halfway between 0 and 0.2. That's where this 0.1 comes from. And this 0.3 comes from halfway between 0.2 and 0.4, etc. And where do these heights come from? Well, we did this one over here. The 0.9 came from 0.9 squared, or 0.81. And I did a few of these for you already. 0.1 squared is 0.01, 0.3 squared is 0.09, 0.5 squared, well, we can square that pretty easily. Or we can square 0.7 as well. So these, again, are the heights of each rectangle. The first height is very short, it's 0.01. The second rectangle has 0.09 in height. The third rectangle is 0.25 in height. And notice that each one of these rectangles crosses, the top of each rectangle crosses through the curve at the midpoint of the subinterval at 0.1, at 0.3, at 0.5, at 0.7. So that's where we're getting the height from, is from the midpoint of the subinterval. As we mentioned before, the width of each rectangle is constant. In this case, our delta x value is 0.2. And if we know the height and if we know the width, then it's easy to find the area of each rectangle. If we're going to find the sum of all of those areas, then we better find each one. So I did the first couple for you, but we can just multiply each one of those by 0.2, and we'll get 0.050, and we're going to get 0.098, and we're going to get 0.162. So that's the area of each of the 5 rectangles. So we're going to add those up. Now, we could just punch those into a calculator. There's no shame in that. But kind of the goal here is to come up with some sort of equation so we can do this for some generic value. So we're going to talk about the ith partition. Not the first, second, third, fourth, or fifth, but any one of these. So we look at this and we try to find a pattern. The 0.1, 0.3, 0.5, 0.7, 0.9. Well, they're going up by 0.2 each time. We're going to add 0.2 to get from here to here. And we're going to add 0.2 to get from here to here. So that's where this 0.2 comes from. That's the rate of change, the slope of that linear progression. But if I equals 1, we don't get 0.2 times 1. We get 0.2 times 1 adjusted by an amount. We're going to subtract 0.1 to get this down to the 0.1. So we can test this for each value. Try to plug in 1 in for I, plug 2 in for I, plug 3 in for I. And each time we're going to get these x values over here. So this is just turning this arithmetic sequence into an equation. Once we know the x value, we know how to find the height. We use the function. And the function, remember, is x squared. So we're going to take x, and we're going to square it. And our width is constant, doesn't matter which partition we're looking at, it's always going to be 0.2. So in order to find the area, what did we do? We multiplied height times width. So we'll have 0.2 times 0.2i minus 0.1 squared. That is your width times your height. So that is the area of the ith rectangle. Okay? And so we want I to start at 1 and go to 5, because we have 5 partitions in this problem. And we're going to say 0.2 times 0.2i minus 0.1 squared is what we're adding up. And again, you can use a calculator for this. You can either manually type in each of these 5 numbers, or you can type in the summation notation. In fact, if it were me, I would probably do both and make sure that I got the same answer each time, because if I didn't, then there's something wrong somewhere. So I'm typing this in as I talk, and I'm getting 0.33. So hopefully you got the same thing. And again, that's going to be the value that we are, this is an approximate value of the area bounded by the curve and the x-axis from 0 to 1.